Linear regression is the most fundamental machine learning algorithm that everyone knows. It's used in practice and asked about in interviews. We are going to go over the concepts that I wish I was told when I first started learning about it. In order to get the full picture of what linear regression is, we are going to split this video into 4 parts. What is linear regression? How the model learns, what the assumptions are, and the pros and cons. By the way, this is part of my essential machine learning topics list that I'm building on my website. Feel free to follow along as I make more videos. Link is in the description. All right, let's get started. Linear regression goes by several names, such as ordinary least squares, simple linear regression, and multiple linear regression. You might be thinking to yourself, ordinary least squares sounds kind of weird. We'll cover that later on in this video. Linear regression is a parametric, supervised machine learning algorithm that tries to fit a line or hyperplane to data. So let's break down what that means. Parametric basically means that it has a model, and that model has parameters that we try to find values for. Supervised basically means that we train the model by showing it what the correct answer should be every time it gives an output. It can then use that information to determine what good values should be for the parameters in its model. And lastly, it tries to find a line that fits our data. Or in multiple dimensions, it tries to find a hyperplane that fits the data. So for example, if our data looks something like this on a graph, then linear regression will try to find a line that fits that data. So now that you have a high-level idea of what linear regression is, let's take a closer look at the model. To do that, we are going to look at the equation for a line, the model for simple linear regression, and then the model for multiple linear regression. So you may know that the equation for a line looks like this: y equals mx plus b, where m is the slope and b is the bias term, or the offset. So we may have a graph that looks like this. So now let's transform this equation into the model for simple linear regression. So in order to do that, I'm going to change y into y hat. I'm going to change m into w, x is going to say x, and then b is going to say b, the bias term. So y hat is the output of our simple linear regression model, and the hat is used to indicate that it's what our model predicts. Alternatively, you'll see y. That just means it's the actual value for the example, not the prediction from the simple linear regression model. And I changed m to w because now it represents a weight or a parameter that we're trying to find. And then b stays b. It's a bias term, but that's also another parameter that we need to find in our simple linear regression model. And lastly, x is a data point that we're trying to make a prediction for. So maybe on our graph over here, on the x-axis, we have temperature, and on the y-axis, we have sales of ice cream. So we would give our simple linear regression model different temperatures as x values, and it would try to predict how many sales of ice cream happened that day, which would be y hat. So let me erase this line for a second. Maybe our data actually looks something like this. And when we first start training the model, maybe it will look like this. So that's clearly a bad representation of our data. We don't have good values for w and b. But as we train it, maybe it'll then look like this, and then it will look like this, and then it will look like that. And at this point, we've found optimal values for w and b. So we know we've successfully trained the simple linear regression model and fit it to the data. Okay, so that's simple linear regression. Now let's talk about multiple linear regression, which is basically when you have multiple independent variables. You have multiple x values in the equation. So let's write that down. Y hat is equal to w1 x1 plus w2 x2 plus dot 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 plus wn xn plus b, where n is the number of independent variables that we have. So multiple linear regression is kind of just like a multi-dimensional simple linear regression. So instead of fitting a line to the data, it fits a hyperplane to the data. If you know some linear algebra, then you can see that this part of the equation is just a linear combination of the x values and the weights. So we can rewrite this equation in simpler terms. Y hat is equal to the weight vector dotted with the feature vector plus b. And I'll draw these arrows to represent that these are now vectors. So instead of fitting a line to our data points, it now fits a hyperplane to our data points. So let's pretend we have two independent variables, so we're working in 3 dimensions. So our graph might look something like this, and then it'll create some sort of hyperplane that fits our data, which may look something like that. And then our data points will hopefully be on or close to being on the hyperplane, something like that. We wouldn't want to see data points away from it like that. So now that you understand the model for linear regression, let's talk about how you can actually find values for the parameters of the model, for W and B. There are 2 main techniques for finding those values. There's the ordinary least squares method, which is basically an equation that allows you to directly calculate what those values should be. And then there's the gradient descent method, which allows you to iteratively get closer and closer to the optimal values for those parameters. I'm just going to touch on these 2 methods briefly, and I'm going to make future videos later that go into more depth. So let's start with the ordinary least squares method. You may also hear this called the normal equation. This is a statistical method for finding the least squares coefficients, which are the parameters that we're trying to find values for. It does this by solving for equations that minimize the squared error between what the model predicts and the correct value for what the model should have predicted. And then those equations are called normal equations. And that's as deep as I'm going to get into it for now. Let's talk about gradient descent. Gradient descent is a fundamental machine learning technique for finding optimal values for parameters. In essence, gradient descent involves looking at how badly your model performs and slowly adjusting its parameters towards more optimal values by taking derivatives of the cost function. A cost function represents how bad your machine learning algorithm is doing. Different algorithms have different cost functions, and the same algorithm can have cost functions written in different ways. Let's write down a common cost function for linear regression. J is equal to 1 over 2m times the sum from I equals 1 to m of y hat sub I minus y sub I squared. So let's break down this formula. J is just the common notation for representing the cost function. M is the number of training examples that we have. It's the number of data points that we have. So you can see that we're going to sum over all of the data points. And then we are going to take the predicted value for that data point, y hat sub I, and subtract it from what the value should have been, the actual value. Sometimes this is called a label. And then we are going to take the difference of them squared. So this formula is giving us the squared error. And the whole cost function is sometimes called the mean squared error, since we're looking at the sum of all of the squared errors and dividing it by the number of training examples. So finding a good cost function is the first step for being able to train the linear regression algorithm with gradient descent. But we need to know what the partial derivatives are of this equation so that we can use them to update the parameters of our model. So let's quickly write down the formula for a simple linear regression again. Y hat is equal to wx plus b. So we know that we have 2 parameters. So we are going to need to get 2 partial derivatives. The first partial derivative, del j del w, is equal to 1 over m times the sum from I equals 1 to m of y hat sub I minus y hat times x sub I. And the second partial derivative, del j del b, is equal to 1 over m times the sum from I equals 1 to m of y hat sub I minus y hat. So these 2 partial derivatives are used to slowly update the model parameters w and b to help them converge closer and closer to more optimal values. Like I said before, in another video we're going to really break down how gradient descent works so you can understand better how it's using these partial derivatives. But for now, I think this is good for you to know in order to get started doing machine learning. One more thing about this cost function that I want to briefly state is that it's convex, which means it looks something like this. It's going to have this bowl shape. You'll hear about this a lot when learning about linear regression, and this just means that the gradient descent algorithm is going to be able to find the optimal value. It's going to be able to easily find the bottom. If our cost function was not convex, maybe it looks something like this, then if it starts here, it will go down and find the bottom here instead of the actual bottom over here, which means it won't find the actual optimal values. Don't worry if that doesn't make sense. Check out the gradient descent video that I'm going to make soon. Now I want to talk about the statistical method versus machine learning algorithm debate for linear regression. But real quick, if you're enjoying this video, please consider subscribing. Also, check out the Discord channel I've made for us to all learn AI together in one place as a community. It's really easy to sign up. The invite link is in the description below. Back to the debate. Is linear regression a statistical method, or is it a machine learning algorithm? This was a point of confusion for me when I first started learning about linear regression. When Googling about linear regression, you're either going to come across statistics websites or machine learning websites. On the statistics websites, you're going to learn about correlation, the R-squared statistic, and the ordinary least squareds method. And on the machine learning websites, you're going to learn about the model and gradient descent. Why is there this division between these two websites? From a statistics perspective, linear regression is a technique to estimate the relationship or the correlation between variables. So that's why you learn about the R-squared statistic and correlation and the ordinary least squareds method. But from a machine learning perspective, linear regression is viewed as a model that we can train to learn a pattern in data. So that's why you learn about models and gradient descent. So there isn't really a debate. Machine learning has its foundations in statistics. So arguably, it's important for you to understand all of these concepts. But I just want to give you a heads up about why you might be seeing different information on these different websites. Now let's talk about the assumptions of linear regression. If you violate some of these assumptions, it's likely that it will not perform well. There are 5 assumptions. Let's start with number 1. There must be a linear relationship. This is kind of obvious because we know that it fits a line to data. So linear regression wants data that looks like this, so it can fit a line to it. However, if our data has a nonlinear relationship, maybe something like this, then linear regression will not be able to fit a line to it. Assumption number 2, there must be homoscedasticity? Homoscedasticity? And that just means that there must be the same amount of variance in your data around the line that linear regression finds. So for example, you want your data to be like this. See how it's all centered around the data. What's bad is if your data looks like this. It has kind of a funnel shape, which we don't want. We want it to be an equal variance around the line of best fit. Assumption number 3, there must not be autocorrelation. Autocorrelation is when there's a relationship between the data at different points in time. So maybe our data looks something like this. You can see that at this point of time, there seems to be a lot of values around here. But at this point in time, there's a lot of values around here. So you can see how there's a relationship between where the data points are at different times of the graph. This is bad. We want all the data points to be independent of each other. So if we have a data point here, this new data point is not influenced at all by the fact that this one is at this point. Then our next data point could be here, and the next one here, and the next one here. None of them are influencing each other. The 4th assumption is multivariate normality, which basically means the data points are normally distributed around the line of best fit. If we have a graph that looks like this, we want the data points to all be normally distributed around the line. So you can see that they kind of form a normal distribution where most of the points are lying on the center, but there's some kind of on the outsides of this distribution curve I drew right here. What we don't want is for it to not be normally distributed, which might look something like this. You can see that the distribution of these data points looks more like this, which is not good. The last assumption is lack of multicollinearity. This is when the predictor variables, or the x values in our equation, have a linear relationship with each other. We don't want that. We only want them to have a relationship with the y variable. the dependent variable. Okay, those are the 5 assumptions of linear regression. Now let's go over the pros and the cons of the algorithm. Some of the pros are that the model is simple and interpretable. It's really easy to understand what's going on, and that it's not computationally expensive. It doesn't require a lot of compute power to run, as opposed to like a neural network. Some of the cons are that there must be a linear relationship among the data. It can be sensitive to outliers, and it struggles when the features are correlated. We just mentioned this is called multicollinearity, and it can be difficult to get rid of that in your data. Gradient descent is another important concept to understand, and the first step to understanding gradient descent is to understand derivatives. So check out the video I put on the screen to understand derivatives for machine learning. I'll see you in the next video.